So I'll tell you about news from the fractional quantum Hall effect, and it's work that has been funded by various usual sources on the other side of the Atlantic Ocean. But since this is we are in the heart of the capital, the center of global capitalism, let me start with an advertisement, a commercial, and I hope you'll forgive me for that. So we'll settle this later. So this talk is going to be about the quantum Hall effect, which is maybe the best or the most well-studied topological state of matter. But it's only one example, and as you probably know, topological states of matter are at the core of research worldwide. Now, with my friends at Weizmann, we produced a course, an online course with about 65 videos. Some of the faces you see may be familiar. Raquel, for example, was here. About 65 videos covering all aspects of topological states of matter, starting from the quantum Hall effect, topological insulators, and going all the way to the Tori code and the more sophisticated stuff. So I'd like to, you can find it on YouTube, and I'd like to encourage you to use it whenever you have some aspect that you'd like to get a good intuition for. Okay, so that was the commercial part, and now I'll get to the content of the talk. So there are three types of news which took place in the last, let's say, 2-3 years in the field, and let me first lead them. One is the observation of the fractional quantum anomalous Hall effect, or the fractional Chern insulator, whatever name you would like to use. The second is the observation of a new series of fractional quantum Hall states, and I'd like to point out they bring to light some new type of physics. And the third involves observing interference of anyons in Fabry-Perot interferometers. Now, I have only 1 hour, I guess, so I'm not going to cover all three. I'm going to try and cover the first two, but I'm here for the afternoon, and if someone has nice thoughts about the interferometer, I'd be happy to discuss. Yesterday, actually, one of the players in this field was interviewed here and probably met a few of you.
No, he wasn't interviewed here. It was from Simon Society of Fellows, which is across the street.
Ah, sorry, he was interviewed across the street.
Yeah.
Okay, I wasn't aware of it.
Well, the problem is we have the kind of separation for states that we have to keep our hands on.
Okay, sorry, I take it back. Okay, so I'll cover the first two. I'll start with a brief introduction and review of the integer fractional quantum Hall effect, and the main goal of this review is to tell you what are these two items of news which I'd like to cover. Then I'll talk about these two items. The half-filled Chern band will occupy the main part of my talk. I'll talk about composite fermion description of the half-filled Chern band, and this is based on a work done with a few friends at MIT, one paper with Liang Fu, and the other with Liang and his group members, Ahmed Abul Kumsan and Denis Sargapol. The last part of the talk will cover these new states, coined the daughter states of the quantized half-filled Landau level. And in particular, I'm not going to get into details in this. I want just to tell you what can be concluded only out of topological considerations. And that's based on a work that I did with two Technion friends, Nathaniel Linder and his student, Evgeny Zheltonitsky. And there was, to our surprise, a competing paper done just across the corridor from my office by Yutoshui Maros and Maria Hermans. And the contents of the two papers is quite similar. We also coordinated submission. Okay, let's start from the quantum Hall effect. You probably know the story. There's a Hall effect, you push a current in one direction, you have a magnetic field perpendicular to, it's a two-dimensional system, magnetic field perpendicular to the plane. You measure Hall resistivity and longitudinal resistivity. And in the 1980s, in 1980, in fact, von Klitzing and his collaborators observed this amazing quantization of the Hall resistivity and vanishing of the longitudinal resistivity. They found that the quantization comes in of the resistivity comes in these units h over e squared times 1 over p. That was coined the integer quantum Hall effect, not because of this expression, but because of the inverse of this expression. P is an integer number, so the conductivity is quantized in units of integer units of e squared over h. In this experiment, I'd like to talk about the resistivity. You'll see why. It became very, very quickly clear. Some of the people here may remember this, I don't. It became clear that this has to do with the existence of Landau levels and a gap between Landau levels and edge states at the edges of the sample and so on. That was 1980. This was reproduced many times ever since. This data is 40 years older than this one. It's from 2023 from the MIT group of Longju. What's the difference between the two? Well, you can see the two obvious differences come to your eyes. First of all, in the 21st century, data comes in colors. Second, you have to put OXX and OXY on the same plot to save resources. You pay now for graphs. So those are two important differences, but not the most important one. The most important one has to do with the magnetic field. So this was taken at 13 Tesla. This was taken at 0 magnetic field. So we have a quantized Hall effect integer at the moment, quantized Hall effect at a 0 magnetic field. Now, back to the 1980s, 2 years after the discovery of the integer quantum Hall effect, the fractional quantum Hall effect was discovered, and it was found that not only that you have this integer p as the topological number describing quantum Hall states, but you also have fractions. And the main series looks like this fraction you see up there, p over 2p plus 1, so that the resistivity OXY is quantized to these values of h over e squared 2 plus 1 over p. Now you can, of course, write this also in this way, 2h over e squared plus the same expression we had at the integer quantum Hall effect. So somehow the fractional quantum Hall effect, when you think about it in terms of resistivity, seems to be the same old story plus 2 h over e squared. And we'll get to it. This is at the core of composite fermion theory for the fractional quantum Hall effect. We'll get to it in a few minutes. If p goes to infinity, for the integer, forget these two. For the integer, when p goes to infinity, the Hall resistivity becomes 0, which is the case for a 0 magnetic field, which is the case for a normal metal with no Hall response at all. So the limit of p going to infinity is a metallic state. And in this particular case, you see at the fractional case that this is the 2h over e squared or the half field Landau level case, which is at least in some cases, as you see in this particular plot from Horst-Tomer, is a state where there is no quantization of the Hall resistivity. There is no plateau as in the integer, as in the fractional and integer quantum Hall states. Now, before I go any further, I cannot not say this. The observation of the fractional quantum Hall effect, that was a first glimpse to a world of wonders. The particles with fractional charges, fractional statistics, the topological protected degeneracy of the ground state, topological order, error correcting codes, what have you. That's really a wonderful part of physics. Okay, back to 2023. So the same group of long Jew at MIT looking at the transport properties of pentalayer ABC rhombohedral graphene put on HBN, whatever, found this. This looks like the fractional quantum Hall effect, right? But again, it's at zero magnetic field. So now not only that we have an integer quantum Hall effect at zero magnetic field, we also have the fractional. This is really fresh data. I think it was taken 2 weeks ago or something. And you see ρxx goes to dips which are pretty deep. They don't go all the way to zero for the quantum Hall connoisseurs. They don't go all the way to zero, but they go pretty low. And what's more important, they go lower and lower with every experiment as time passes. So and you see the plateaus up there in blue, and you see that at some point there's also an integer quantum Hall state that kind of takes over this series of fractions. Now, maybe I should have said, you see here ρxx in red, ρxy in blue. Now, it's not as a function of magnetic field, because there's no magnetic field. It is a function of the filling of a single band that's filled in the system. Okay, again, the half-filled Chern band, this 0.5, is a compressible state, no fraction, no plateau, and no dip of the resistivity going to zero as here or here. I should have said, please feel free to stop me at any point.
So this is newer data. There was data about a year ago that they had RxY1 on the pentalayer. That's been superseded.
Yeah, no, so it didn't go all the way to 1, but it was far too high for our taste. It was like 0.25.
Your taste or the experiment?
No, the old experiment, ρxx was too high also for me. This is the new data. This is my understanding, what they're telling me is we just get better at this. We know how to deal with the sample. Anyway, that's the new data. Yes.
By the way, I assume it's in this print. It looks like at the 2/5 state the resistivity RxX is less than 0.
That
At 2/5 RxX would be less than 0.
2/5. Yeah, right. It's probably, I don't know. Imagine.
That would be a mistake.
Yeah. That would be would solve the world's energy problem, among other things. Would make me.
Just for general, I've been meaning to catch up.
Mm-hmm.
How big is the
How big are the samples? A couple of microns.
Mm-hmm. And so this is sort of low enough temperature. They document this is the residual value.
This is 30 milliK.
There's no.
This is 30 milliK. There was an issue with temperature. Maybe I'll get to it. But this is the 30 milliK now. It's linear response. Yes. So that's the news item number 1 that I'd like to talk about, and I'll talk about the half-filled state. Okay. News item 2 is completely different. It's the traditional quantum Hall effect, namely with the magnetic field. People look at RxX, RxY, and what it has in common is this magic number of half-filled something. So here it's a half-filled Chern band. There it's going to be the half-filled Landau level. Now you see that's data from all groups all over the world. Sheyegan in Princeton, Zhu in Penn State, Andrea Young in UCSB, and my colleague Yuval Ronen at Weizmann. Let me focus on one. Even one has too many lines. What I'd like you to pay attention to is that this is a case where the 1/2 state has a plateau. So we know there are cases, and let me not make the distinction now. There are cases where the 1/2 state is compressible. That's going to be the first, the next, let's say 20 minutes. And then there are cases where the half-filled state is incompressible, OXX going to zero, plateaus in OXY, and that will be the later part of the talk. What the main thing, the main point here is not the observation of a plateau at the half-filled state. That was done before, that happened before, but the states around it, the states you see as you move slightly away from half-filling are different in this case than they were before. So you don't see the P over 2P plus 1 anymore, you see something else. And we'll get to this. So those are the two news items. As I said, there's also interferometry, and I'm not going to get into it. Okay, the half-filled Chern band. Quantum Hall effect with no magnetic field, and in particular, fractionally quantized. How do we think about this? Okay, so this was the background up to now, and now I'm getting to what I want to say. So first of all, let's compare these two effects: the traditional Hall effect under a magnetic field, and what's called the anomalous Hall effect at zero magnetic field. So this slide is all from Ashcroft's mem in chapter 1. You probably either learned it or taught it. And what you know is, do you have a so I have a laser pointer, but those are hardly seen. Never mind. Don't worry, Andy. The theory of the traditional Hall effect comes out of Drude theory. You write basically Newton's equation of motion and allow for momentum to relax. And you find the resistivity matrix, a DC, that has longitudinal resistivity, which doesn't know anything about the magnetic field, and a Hall resistivity, which is all about the magnetic field. And the total resistivity is the sum of the two. Now, if you have no impurities and work at finite frequency, then 1 over tau is replaced by I omega. But again, you add the longitudinal resistivity and the Hall resistivity. Now, if you are interested in excitation modes, one possibility to find excitation modes is to look at the zero determinant of the resistivity as a function of frequency. When the determinant has zero resistivity, it means that you can have currents flowing without having an electric field, which is an excitation mode. And you do this exercise here, you find the plasma excitation at omega equals omega c, just the cyclotron mode, Cohn's mode, and it comes out of the fact that electrons in a magnetic field go around in circles with this particular frequency. Now, this is the traditional Hall effect. The anomalous Hall effect is somewhat similar, somewhat different. So let's see. It comes out of the fact, the equations of motion. We started over there in the Drude theory with an equation of motion. Here we also start with an equation of motion. The first equation of motion is just Newton's second law. The momentum changes according to the force that's acting. But the place where things change is when you look at the equation of motion for the velocity. The velocity has a new term, which is proportional and perpendicular to the electric field. And with the proportionality constant being the Berry curvature determined by the properties of the band that the electrons live in. So now the whole response comes not at the level of an equation of a force relation, Lorentz force versus momentum, but at the level of a contribution to the velocity. Now, that means that you have an anomalous Hall conductivity because you put an electric field and the electrons move perpendicular to the electric field. For a full band, you get an integer quantization of the Hall conductivity, and this is called the Chern number. Talking about Chern in the Simons Foundation or Simons Center, is an experience I never had before, let's say. I'm not going to mention Chern-Simons theory here, but it's all over the place. There's an integer quantization of the band, and that's the Chern number. But for a partially filled band, we can write a semi-classical expression for the conductivity, and it's different. It's different from the whole one, because now look what happens. The current is the integral over all occupied states of the velocity. Okay, all occupied states of the velocity. And the velocity has this whole contribution. So what happens now is that we sum conductivities. The longitudinal conductivity coming out of this usual contribution to the velocity is the usual thing, is the usual Drude expression. Here, D stands for the Drude weight, not for the diffusion constant. And I emphasize this because it will come back. So the longitudinal conductivity doesn't know anything about the Hall and the Berry curvature and all this, and the whole conductivity doesn't know anything about tau, about the scattering. So now we add conductivities. And you know, when you add conductivities or you add resistivities and you start inverting 2 by 2 matrices, things may happen, and we'll see that. Now, when do we see a zero field Hall effect? So, you know, time reversal symmetry must be broken. The way it's, and you know, typically typically this world is time reversal symmetric. So in 2 years from now, you may look either older by 2 years or younger by 2 years. But in these samples, it is usually time reversal symmetric. Anyway, you know that the way these things are done, you know, nowadays is looking at Morse systems. Morse systems break the electronic bands into many mini bands, and then we have a Chern band with a certain Chern number +1, let's say, at one corner of the Brillouin zone, and -1 at a different corner of the Brillouin zone. And now the only thing you need is to somehow talk the electrons into occupying only one of them and not the other. And that's not something for us to be doing. That's done by a kind of Hunsul philosophy, spontaneous breaking of time versus symmetry in order to minimize on exchange energy. And there are two main examples for this. One is the twisted molybdenum tellurium 2 bilayer, and the other one is the pentalayer graphene on HBN. I think there are also observations at the other number of layers of graphene. Anyway, to summarize this story of the traditional and anomalous Hall effect, as I said, in one case you sum conductivities, in the other you sum resistivities. One consequence this has is about the plasma mode. So the plasma mode in a magnetic field is at the cyclotron frequency at omega c. That while the plasma mode for non-interacting electrons in a partially filled Chern band, those are just electrons in a band, and there is no cyclotron motion, there is no Lorentz force, and therefore the plasma mode disperses from zero frequency at zero momentum. I emphasize this because it will be important later. Now, in terms of what happens at the full band, as you saw, you get the same quantization. Okay, now what happens when the bands are partially filled in the Landau level case and in the Chern band? So here comes another difference between the two problems. The problem of Landau levels, the fractional quantum Hall effect, and the problem of partially filled Chern bands. And here's the difference. In the first problem, the one of Landau levels, you know, the Landau levels have a zero width, and therefore we have only two energy scales in the problem, only the interaction energy scale and the energy gap between the consecutive Landau levels h bar omega c. So no matter how small the ratio between these two is, there are only two energy scales, so there's only one ratio. For infinitesimal values of this ratio, we still expect to see a fractional quantum Hall effect. Okay, at zero temperature, in the absence of disorder, all this. But at the level of principle, with the fractional quantum Hall effect should occur at infinitesimal interactions. That's not the case when there is no magnetic field, because now we have bands, and the bands have also a bandwidth. So now, if the bandwidth gives us another ratio, and if the interaction, if the band is partially filled, no matter what partial means, 20%, 30%, 40%, any number, if the interaction is too weak, we just have electrons in a band, fermions, weakly interacting fermions in a continuous spectrum, gapless spectrum. This is, they are subject to the Landau Fermi liquid orders, and they'll just form a Fermi liquid of electrons. And there will be no crucial dependence on the filling. Now, but if the interactions are stronger than this energy scale, then there's a room for something new, and that's where we will see this FCI stands for fractional channel insulator with a strong dependence on the filling. So how shall we analyze this second limit using composite fermion theory? So composite fermion theory was constructed to understand the partially filled Landau level, and it follows the decades long, centuries old habit of people in our profession, which is if you have a very difficult problem you don't know how to solve, you map it onto a different problem and you hope for something good to happen. Maybe you will know how to solve it. Maybe you'll be able to approximate it in a better way. Maybe you'll just come back. Then you kept yourself busy. So that's the idea, and that's what this is. It's a mapping from electrons at the magnetic field B with some Coulomb interaction to different particles, composite fermions, at a reduced magnetic field delta B. And delta B is B minus 2 flux quanta times the density, which means every electron, in order to be transformed to composite fermions, is attached or is given 2 flux quanta to carry on its back. This is an exact transformation. And we know how to do it. It definitely maps the problem from a difficult problem to another difficult problem, but it opens the road for a natural approximation. So the first step is exact. The second step is just a mean field approximation, and it takes the flux that's attached to the electrons and spreads it uniformly on the sample, just like a Hartree approximation spreads the charge of each electron on the entire region, around the nucleus of the atom in the first use of this. So then you reduce the magnetic field. You reduce the magnetic field, you change the filling. And if you do the calculation, you find that you map the filling of P over 2P plus 1, which is the filling where the fractional quantum Hall effect was observed, to an integer filling. So the fractional quantum Hall effect of electrons is mapped onto integer quantum Hall effect of composite fermions, which means it does only one good thing for us. It gives us a natural starting point to think about an energy gap. Why there is an energy gap. And that starting point is the integer quantum Hall of the composite fermions. Now there's a price for that, and the price is the resistivity of the composite fermions is not the resistivity of the electrons. If you calculate the resistivity of the composite fermions and find some value, you need to add this 0, 2 minus 2, 0 multiplied by h over e squared in order to get the resistivity of the electrons. Now, adding two matrices is pretty easy, particular with all this zero. If you want to calculate the conductivity, then you need to add this and then invert. Still 2 by 2 matrix. When we'll see examples very soon. Okay, now, yes. Here, the flux attachment.
Lower right.
Yes, I would say yes. So it's technically it's geometric. It's almost a definition, basically. It's saying that the electronic conductivity, let me write it as interconductivity, will be this plus, I'll define this in a second, plus this, and on, where this is the sigma of the composite fermions, and this is I get to mention the founder of this place. This is the Chern-Simons interaction. So that's an exact, restructuring of a sum of diagrams, and that's this. It's a geometric series, and that's this. Okay. Now, as everything. No, so. I don't know how I exactly define No. Okay. Fine. I would be willing to accept this definition of the composite fermion, probably. It's more or less a definition. I'll show it in a second, but this is not RPA. This is not non-interacting composite fermions. This is anything that's irreducible with respect to a single Chern-Simons line. So in that sense, it's just a restructuring of sum of diagrams. Yes, it's very similar. Yes. So yeah, I misled you, Leon. Apologize for this by drawing this as an empty bubble. It's not empty. It includes everything. But it's irreducible with respect to a single Chern-Simons line. And that is the definition of the composite fermion conductivity. Okay, then you can approximate it one way or the other. Yes.
All right, and just to make sure, you're going to tell us how to do this on the lattice?
Yeah. We still have a lot of time. Okay, just to show how this is done. I won't do it much. You probably saw it. Many of you saw it before. How exactly the composite fermion transformation is done. You write the Hamiltonian for the electrons. You define a new wave function that's related to the old wave function by a phase factor, a singular phase factor, whose physical significance is the attachment of two flux quanta to each electron, and that changes the kinetic term of the Hamiltonian to have a new vector potential whose curl is the 2 phi naught times the density that I mentioned before. Okay, I'm rushing over this, but if you would like me to be slower, just let me know. This is the same story, but now in pictures. If you decide not to read the book but wait for the film, this is the electrons in a magnetic field. Those are the two flux quanta. This is the spreading of the two flux quanta uniformly over the region, and the magnetic field is reduced, and therefore also the filling factor of the composite fermions is different from that of the electron, and the resistivity is similarly. Now, there's one crucial point here, and this is at some particular filling factor, 1/2, the residual magnetic field that's left is 0. So at this particular filling factor, delta B is 0, and we map the electrons from the half-field Landau level onto composite fermions at 0 magnetic field. And composite, fermions at 0 magnetic field, that's the devil we know. That's Landau's starting point. Does this work? You go to the experiments, and in gallium arsenide before the days of graphene, for half-field Landau level and 3 half-field Landau levels, it works really nicely. For 5 halves and 7 halves, you have to put a twist to this. The composite fermions form superconductors, and we'll get to that at the last part of the talk. And above, it just doesn't work. There's a different phase that takes over. So the answer to the question, does composite fermion theory work? The answer is like any good theory, sometimes yes, sometimes no. Now, how are we going to do it in a Chern band? So, the whole of this flux attachment story of attaching 2 flux quanta and then spreading the magnetic field was to cancel the magnetic field. Right? This is why this is why it was done some decades ago for the fractional quantum Hall effect, because the idea was to reduce O for 1/2 to completely cancel the magnetic field. Now, that's the trick we have at our disposal. We're going to do it. But you cannot cancel something that does not exist, right? So we are going to attach 2 flux quanta to each electron and spread the flux quanta uniformly, and they're not going to cancel anything. They're going to generate a magnetic field. So we map from electrons at filling factor nu, meaning new electrons per site in the Chern band at 0 magnetic field to composite fermions at same filling factor, but with a magnetic field, now with the magnetic field which we introduced, 2 phi naught times nu. Why is it a good idea to put in a magnetic field in this problem? The answer is of 1/2. Okay, let's separate the 2 cases. If nu is a fraction with q being odd, so a fraction with an odd denominator, then what happens is with this, the introduction of the magnetic field makes the unit cell grow q-fold, multiplies the unit cell by q, which means it takes the band and breaks it into q subbands. And the q subbands are separated from one another by an energy gap. So that gives us, again, like in the older case, it gives us a starting point to think about how an energy gap can emerge. So this is for this case. It gives us a way to think about an energy gap. Now for 1/2, the attached flux, the flux that you attach, 2 flux quanta per electron times 1/2 electron per unit cell is 1 flux quantum per unit cell. So the unit cell does not grow. So you map the problem from a half-field Chern band to a half-field other band. Maybe Chern, maybe not. But you map the problem from a half-field band to a half-field band. That sounds like wasting your time, right? I will try to argue that there are conditions where that's the right thing to do. But for the moment, just let's do it. Okay, so now focusing on the half-field Chern band, what this line of thinking tells us is that there will be 2 different regimes. The regime of weak interactions, we will have just electrons in a half-field band, weak interaction. They will form a Fermi liquid theory. It will not be very different if it's 1/2 or 0.45 field. It will have a conductivity sigma and resistivity rho, which we analyzed before. The conductivity of and resistivity of electrons in a Chern band. In the strong interaction case, we will get a compressible state of composite fermions. Now the resistivity will be the sum of this plus this. And this will be pretty much like what the, like a conductivity of a half-filled band. But now, to get to the electronic resistivity, you will have to do this exercise. Now, Valentin here and Harvard at MIT, I think at the time, right? And Harvard group already discussed something like that, but we took it to a different direction, which I'll mention, which I'll now describe. So let's compare the two phases. Very quickly on DC transport, but I'm more interested in AC transport, and that's what we'll get to. So in DC transport, questions? Or? So DC transport, the conductivity, as we said before, is the sum of conductivities, which means if the sample is clean, and let's assume the samples are clean, 21st century, everything is clean and so on. The conductivity is dominated by the longitudinal component. Now, this is not like what happens for electrons in a magnetic field. For electrons in a magnetic field, everything is Hall response, right? So the off-diagonal elements dominate both the resistivity and the conductivity. For electrons in a partially filled Chern band, everything is dominated by the longitudinal element, and the off-diagonal element is minor. When you invert to the resistivity, and you need to invert because experimentalists usually measure resistivities, you will get a small resistivity dominated again by the longitudinal one. In contrast, when you add this 0, 2 minus 2, 0, then you're dominated by this. So the two phases will be very, very different. And this one will have a small diagonal resistivity, but a large Hall resistivity close to 2h over a squared. Now the experiment, what you see here, I cut the left part and I'll tell you why. What you see here is the resistivity. This is Hall and this is longitudinal as a function of displacement field. Displacement field is the voltage applied to the pentalayer, an electric field applied from a bottom gate. And it's kind of a proxy to changing the bandwidth. We cannot change the interaction between electrons, at least we cannot easily change the interaction between electrons. So what we'd like to change is the bandwidth. So this is a proxy to changing the bandwidth. What happens on the left side, I took it off because it's all insulating state that involve breaking of translation symmetry. But what you see here are three phases, right? This is small Hall resistivity and small longitudinal resistivity, and this is just the electronic phase I was talking about before. This is, sorry, I shouldn't have cut the left part. This is the 2h over a squared, Hall resistivity and pretty small longitudinal one. This is the composite fermion phase. And what you see here in the middle is an intervening phase of an integer quantum Hall state of 1, and you see as a function of temperature, the longitudinal resistivity goes to 0. It's an incompressible state, and I'm not going to discuss it now. All 1/2. From now on, all is 1/2. Sorry, yeah, I should have said it. 1/2. Okay. Now that can get you, this analysis can get you some predictions about temperature dependence, which work well with the experiment, but let me not get to it, but talk about AC transport. So let's take, the mean free time to infinity and the frequency to be large, and talk about AC transport. And the first question I'd like to discuss is cyclotron mode or plasma mode. Okay, so what did we say so far earlier in the talk? Electrons in a magnetic field have a cyclotron mode which is gapped. The plasma mode is gapped, omega c. Electrons in a Chern band do not go around in circles and therefore do not have a gapped cyclotron mode. They have a gapless plasma mode. They form a metal. And a metal, a zero magnetic field, why shouldn't it have a gapless mode in 2 dimensions? What about the composite fermion phase? So you need to look to calculate the resistivity and take its determinant and as a function of frequency and see if it ever becomes 0. So it's this exercise. You write the determinant of this 0, 2, minus 2, 0. This time I do have the h over e squared. Sorry for the inconsistency. And the resistivity matrix for the composite fermions. You calculate this on 2 sides of the ocean and both manually and with Mathematica, and you find that there is a gapped excitation mode at some frequency, never mind what it is. So this I think is a remarkable property of this state. Forget the description, the composite fermion, the walls, even the name Chern. Forget all this. We have electrons in a partially filled band, and they don't have a plasma mode at 0 frequency. They have a plasma mode at a gapped frequency. Not because of the electron-electron interaction having long range. It has nothing to do with this. And not because of having a magnetic field, because we don't have a magnetic field. So, and yet the plasma mode is gapped. So that's I think a very interesting property of it, and it comes together with a vanishing Doodle weight. So if you calculate using this story, the sigma xx, the electronic longitudinal conductivity of the electrons, the measured one, as a function of frequency, in the absence of disorder, you find that it starts as I omega. Now, you know, for electrons in general, conductivity starts as the Doodle weight divided by I omega. Here, this does not exist, and you start from I omega. So it's a metal that does not really conduct at Q equals 0 in the absence of impurities. It's compressible, but its coupling to the electric field is strange. And now, so you can calculate the Doodle weight. All this was based on this composite fermion, line of thinking. But you can just calculate the Doodle weight by exactly diagonalizing, taking, a finite size system, Chern band with some number of electrons, and calculate the conductivity, the Doodle weight. You don't calculate it by calculating the conductivity, by using a trick introduced by Kohn many years ago, but you can calculate it, and this is what we get. So here you have V naught is the bandwidth, and U naught is the strength of the interaction. And those are 2 different system sizes. Look at the larger size, which is the red dots. You see that when the interaction is weak, which is this side, the Doodle weight is non-zero. When the interaction is strong, which is this side, the Doodle weight is 0. So we have a compressible gapless state with a 0 Doodle weight. My intuition for this is, the calculation was done with this great MIT group. My understanding, one thing, my way of understanding is unlike the Fermi liquid at weak interaction, at the strong interaction, basically half-field level means the occupation number as a function of position is 1/2 for all states. Then when you put an electric field, you hardly do anything to this occupation.
Symmetry across. No change of symmetry at all.
No.
Interaction, but that line is like coming in non-analytically here.
To here, on this side, you say? Or on this side?
Well, both your red and blue are they discontinuous around 0.65 or 0.7?
That's a question I'd like to know as well. Numerically, at the moment, we cannot decide this.
What is the numerics then? What is
Exact diagonalization, ground state energy, the second derivative of the ground state energy with respect to the twisting boundary conditions is the Drude weight. That's Cohen from so that's what.
So deciding from ED on the order of the from really a level cost.
It's a level crossing.
There's no way we can.
That's.
I also would like to know the answer.
Yeah, I also would like. Yes.
And just if you were yeah, I guess having a finite Drude weight, naively I would think that that's a proxy for having a finite quasi-particle residue. Is that right? So because it's a Fermi liquid, everything is kosher.
Well, you can have a non-Fermi liquid with a vanishing residue,
Right.
and still have a Drude weight.
So in this case, I guess my question was going to be: is there any way to look at the quasi-particle residue from exact ground state? You can just.
So looking at single particle grain function, I think what happens is mostly that it decays very fast as a function of energy, but so it's not easy. You can look at the occupation number, n of k, and it does what I just said. It spreads over basically the entire set of states that's available to you here. Now it's a small system, so it's not that many states.
It only does it on the left side and not so.
Only on the left side. Yes, only on the left. No, this is a Fermi liquid, just like in an undergrad. Yes, Leon.
Yeah, I mean, this vanishing I would think compressible. I think on both sides.
Okay, we'll have to think about orders of limits. So in principle, if you move from 1/2 to 0.51, you are in a fractional chain insulator, and then there's a gap. But we don't want that because if there's a gap, the answer is obvious. Yeah. And with this order, you cannot define the Drude weight. So it's. Yeah, so it's a very good question, which I don't have a 1 minute answer to. I'd love to discuss. Probably. That's what it must be. It's a many-body matrix elements, which yes, it's a Q equals 0. So if you. Yeah, so maybe instead of moving away from 1/2, if we move away from Q equals 0, then we'll have a conductivity. So it's a Q equals 0 property. So in that sense, it's very, very fragile.
But you are saying that you approach this CFL state, if I do consider varying carrier concentration, just like we should consider for the moment. But if I do consider that, what you're saying is that we approach this by a sequence of higher and higher order
FCI. Yes.
So this is like this endpoint of this weird series.
Yes. Okay. Yes.
Right.
Yes.
Now, one other thing. So we're coming up on 5 minutes to 12. So we should plan a little bit for what else you want to cover.
Yeah. Okay.
Maybe we should find, except if there are very burning questions of clarification, we should let Adi go on.
Burning? Anything? Okay. Yeah, I'd like to tell you, I told you one AC property, which is this plasma mode. Another one, we were looking at the zeros of the determinant of the resistivity, and then I realized, we realized that there's also a zero, there are frequencies where the conductivity has a zero determinant. So then we asked, what good does it do to anyone? What physical significance does a zero of the determinant of the conductivity have? And the answer is, it has to do with, I'll give you this back in a minute. It has to do with a reflection of radiation that's irradiated from, from above. Here it's in a more prepared way. This is a two-dimensional system, somewhere between 2 and 5 layers, atomic layers, so very, very thin. You irradiate it with a linear polarization electromagnetic wave. You ask how much is reflected, how much is transmitted. It's an exercise in ENM 101. The reflection, you expect it to be very weak because it's a very thin system. And indeed, it's proportional to the fine structure constant. By the time you solve this, electric field should be continuous, magnetic field not, all this. But when you look at this, you can ask what happens to the reflected part when the conductivity has zero determinant. And what you find is that under this condition, there is one circular polarization that's fully transmitted, and one circular polarization that's partially transmitted, partially reflected, partially transmitted, which means you shine with linear polarization, you get back only one circular polarization. So it's kind of a chiral mirror. You send the linear, you get reflected in one. This will happen both for the electronic phase and for the CFL phase. But for the CFL phase, it turns out when you do all the math that, yes, this is still a weak reflection proportional to the fine structure constant. But the proportionality constant, proportionality factor may go to infinity. So there is a condition for the composite fermion properties, never mind, I won't get into details. There is a condition where you shine linear dispersion and you get back 50% of the intensity all in one direction of circular polarization. Do composite fermions make sense for this? I think this is not the right question. I think the right question is, when do composite fermions make sense? And I think the answer is this. So we're talking about strong interaction, right? For weak interaction, we already said the electrons form a Fermi liquid. So for a strong interaction, it means we have a narrow band. Now we do this flux attachment, and we map the half-filled band to another half-filled band. When the second half-filled band is very wide, when the first one is very narrow, and the second one is very wide, the electrons will not be able to form a Fermi liquid, but the composite fermions will. So I think that this is the condition for when this flux attachment approach will work. When it maps from a narrow band to a very wide band. And there's an example for this in the case of MOT2. So this is a calculation done by Christophe Collard, Ken Young, Felix von Oppen, and Christophe Mora. And you see they take a very narrow band. This is just a single particle band structure calculation. You attach one flux, you put it in a magnetic field of one flux quantum per unit cell, and the bands become very, very broad. So, Andy, do I have 7 more minutes?
Sure.
Okay.
5 minutes we could do it.
Okay. This was my story about the half-filled Chan band, and I'll take 5 minutes, if it's okay with you, to give a kind of a long-distance glimpse on the issue of quantized half-filled Landau level. So now with the magnetic field. So we said that if we have a compressible half-filled Chern band or Landau level, we get this Jane series of P over 2P plus 1. But if you look at experiments, and I showed you, the 1/2 state is not always compressible. In fact, sometimes you get an incompressible, a quantized Hall state at half filling. How do we understand it? Well, here's the example which I showed you before. Here, the Hall resistivity does not show anything close to half filling, does not show any plateau, while here you see very clear plateaus, again at the half-filled Landau level. So this is the Princeton data from Social Hagen's group. So here we have the Jane series of P over 2P plus 1. What's going to happen here? How do we understand this quantized state? Well, the way we understand it, the quantized state is a superconductor of composite fermions. So, the composite fermions pair up and condense to a superconducting state, and the description of the superconducting state, or this superconductor of composite fermions exactly maps onto an electronic quantized Hall state at a half-filled Landau level. But then we can ask, what happens as we go slightly off from 1/2? So what happens to a superconductor, in this case of composite fermions, but to a superconductor as we move slightly, as we put it in some residual magnetic field, not, to start with weak and then large and so on. So what happens to a superconductor in a magnetic field? Of course, this is not something I should, keep you waiting for lunch for, because everyone knows what happens when you put a superconductor in a magnetic field. There will be vortices, and as long as the magnetic field is weak, there will be an abrikosov lattice of vortices. And usually what happens is when you make the superconductor, when you make the magnetic field stronger, the Cooper pairs break and the whole thing becomes normal, and you can you can forget about superconductivity. But what if the Cooper pairs are strongly bound? Let's say that they are spin polarized, so the Pauli limit does not impress them. So what if the Cooper pairs don't break and you make the magnetic field stronger and stronger? Basically, this is the story, we believe, of those states. And that's what I'd like to tell you in 2 minutes. So we want to start from a superconductor at a half-filled Chern band, the half-filled Landau level, superconductor of composite fermions, and consider what happens next to it. However, a superconductor at zero magnetic field is not a one-to-one definition of a state of matter, because superconductors with broken time reversal symmetry are classified by a Chern by a Z Chern number classification. Namely, they carry an integer topological invariant, which is for the superconductor the number of marijuana modes that goes around the superconductor, and that number can go anywhere from -infinity to +infinity. So if I'm asking what will happen to such a superconductor, be it of electrons or of composite fermions, doesn't matter. What happens to a 2D superconductor in a magnetic field? I should at least start by telling you, in the absence of the magnetic field, how many marijuana modes are there. Now, for 2 cases, what's called the Pfaffian and the anti-Pfaffian states, this was considered by Michael Levin and Bert Halperin some years ago. And what we did was to generalize this to any Chern number. And the outcome, I will not tell you the technique, I will just tell you the outcome. The outcome is, so again, let me tell you what the problem is, because I know it's the last few minutes of the talk, so I should be clear. So we have a superconductor at zero two-dimensional superconductor. At zero magnetic field, it has C Majorana modes going around it. We now start putting a magnetic field. We have an Abrikosov lattice of vortices. At some point, this lattice melts. What are we going to get? What state are we going to get? What we find is that we are going to get a state that's made of two components in parallel. One is a fermionic quantum Hall state of the C from which we started. So the superconductor, even after it completely lost superconductivity, still remembers what type of superconductor it was. And in parallel to this, a bosonic integer quantum Hall state of 2m with m being an integer. And that composite boson integer quantum Hall state is made of pairs of composite fermions. So it's a new type of state. This is a conclusion we get to only by topological considerations, which do not allow us to conclude about the properties of this state. You know, the conductivity at various frequencies and wave vectors, typical length scales, and all that. And basically, we're in a need for an Hamiltonian that will show this how this structure emerges. But this is what we got for composite fermions, and this raises the question now. You know, nowadays, every other week, some experimental group on one of the two coasts of the US finds a new superconductor in some van der Waals material. Can any of those survive superconductivity to go into a transition from a superconducting state to a quantum Hall state? This will be something that we haven't seen so far, and maybe we will. I'll skip this, and those are my conclusions, and thank you for your patience.
Thank you for this beautiful talk. I'm sorry we got to truncate it. You'll have to come back soon and give us another talk. But in the meantime, we have a couple of minutes for questions before we
What about this proposal that you send linear polarized light and you get there an experiment going on proving that?
So Long Ju is interested in that. He does terahertz frequencies, and Sangfeng Wu at Princeton also. But so people are interested. People who do mostly terahertz spectroscopy.
That would be a mutual.
I would say some multi-layer of graphene and the MOT2. So, you know, Xiaodong Xu, listen, many people say they're interested, but there is the step of assigning a student to work on this or a postdoc. And that.
You also need a thick sample with many layers, because I mean, if there was just one sheet, there's not very many electrons.
Yeah, but you know, reflection of 1% is something that can be measured.
Change of a tiny fraction of a percent
is observable.
Are you not specifying by that experiment the symmetry broken? Because I can think of a dielectric function, a dielectric tensor, which will do what you're saying must happen.
Yeah, so it's time reversal broken. This is so you need a Hall conductivity and a longitudinal conductivity with a particular frequency dependencies. But number one is you need a Hall conductivity.
But again, you're talking about finite frequency.
Right, absolutely.
Not the limit of
yes.
usual.
Yes, right. The usual DC conductivity is the Duder weight tells you the difference.